Hi, everyone, and welcome to season 2 of Training Data. A lot of people didn't think we were going to get past our first episode, me being one of them, but here we are, and we couldn't be more excited to kick off the new year with you. It's important at the beginning of each year that think about the resolutions you made. I know for me, one of my resolutions is to make even more podcasts. And hopefully you feel the same way. And I couldn't think of a better way to start this season with the topic we're going to discuss today. You know, going back to the founding of CosmiQ several years ago, one of the big questions that we heard constantly, and Adam can tell you these stories just as well as I can, which is, you know, how much training data do we need? Right? We hear a lot of sort of random numbers being thrown out. Some seem perhaps defensible, some not. And yet it was very hard to really quantify what was necessary from a model perspective and point to it as a point of justification for continuing to build data sets and spending money or not. And what's really interesting is over the last year, Daniel Hogan on our team and Adam Van Etten, they helped put together a project, not just breaking apart this question, but really trying to answer it in a meaningful way, leveraging some of the data sets that we've built and used over the course of the years. So first, as I've referred to him often, and I think it's been verified on social media at least twice, is the computer vision grandmeister himself, Adam Van Etten. Welcome back.
Thank you.
And we have CosmiQ's newest member, and this is his first podcast. So I think this is a good omen for the year to have our newest member on his first podcast in the beginning of 2020. Is Daniel Hogan. Welcome to the show. All right, so before we dive into the details of this project, let's start like way at the beginning, which is really the motivation for this. So as I said, this is a question that every research group tackles with. And even more than research, when a group is productizing certain ML solutions, they have to think about how to build out an increasingly diverse data set. So when we were unpacking this project, what was our motivation, guys? More specifically, why does this really matter from a business perspective? Why do this type of deep quantitative analysis to see the impact of training data size on something like a model's performance?
So this matters because this is one of the first things that you have to face when approaching a deep learning project. And your metaphor of the chicken and the egg is exactly correct. You have to collect your training data to begin training. That has to come first. But you don't know, in some sense, how much you really need until you've collected it, you've done the training. So how does someone break out of this loop? And the way you break out of the loop is to step back and really study this topic as we've had the chance to do here.
I think there's another piece, which is we've talked a lot about SpaceNet on this podcast. And one of those issues is we keep getting data for SpaceNet, and we're pretty excited about all that. But how much do we actually need, right? Do we need to keep gathering data? Do we have enough to do the type of problems we're tackling, or do we need way, way more? So that's another tactical piece where just we want to know, just for our purposes, right? Is SpaceNet enough for the kind of problems that we're trying to solve, right?
Yeah, and that's both are really good points, and even particularly Adam with your comment. You know, one of the things that we've heard a lot just in the last couple of events that we've either presented at or hosted workshops at, I'm thinking of going back to December where we were at AWS Reinvent. A lot of the questions we got were from participants or attendees asking us what other data sets are coming next. And as you guys know just as well as me, there's always a massive interest to go off and move into the newest data type or a whole new modality potentially. And all those things have merit, but they have a particular merit if we've thought through and quantified if we're providing sufficient data for perhaps one geographic area already. So this is essential both for our operations and for really any organization that's thinking about acquiring more data or building out a robust internal data labeling campaign and trying to justify some of those costs. And so before we kind of get into how we structured our project and experiment, I'm just kind of curious because this was something that we've talked internally on the team a lot about over the years, and I kind of had my own expectations. But what were some of your expectations at the beginning of this project? Because I think a lot of like the standard belief would be, as you decline training data, like this model performance is going to tank, and that's kind of self-evident. So, any expectations out of the gate on this before you got started?
I think an expectation that I had was that over the typical sort of range that we would be looking at, we would be seeing largely, if not exactly linear, at least in the neighborhood of linear responses in terms of how performance varied with the amount of training data that one has access to. And what we ended up finding was quite different, as we'll get into in some more detail here.
Yeah, I'd actually agree, Daniel, that I thought it would be fairly linear for a large portion of the range that we're looking at. And just to kind of drive home the issue that you brought up earlier, Ryan, that, why do you care about this, right? One of the things we've heard a lot is that, there's never enough data, right? You hear that a lot. It's a truism at this point, right? Another thing we've heard a lot is people say you need 1 million data points to do anything useful, right? And I think that number is pulled out of thin air, but we just wanted to figure out what that was, right? Is it close to 1 million? Is it less than 1 million? Is it way less than 1 million? And it matters because training data is expensive, right? Not this podcast, but the actual data that's used for training.
This podcast is a public service to everyone,
it's
so
true.
Cost does not matter in this case.
No, it doesn't. So I mean, even say you make the assumption that labeling one piece of data is 50 cents, which actually, in the whole scheme of things with validation, would be quite cheap.
I would take that deal right now.
That would be great. That means if you need 500,000 labels, right, that's $250,000 right there. Do you want to spend your budget on gathering more data or on something like maybe paying your data scientists? The cost adds up real quickly. And so knowing where you start to asymptote, or if you asymptote, is critical if you have a reasonable budget and you're trying to build something that could be deployed.
And so with that in mind, how did you design this experiment? Because as Adam has mentioned, we hear sort of these random numbers thrown out a lot, or we hear people say it's this proverbial chicken and egg thing. And the problem is kind of gets kicked down the road. I'm curious, how did we design this? And like all things, all data science projects, they start with the data set first. So why don't we go there? So what data set did you use? Why was it appealing? And how did that influence perhaps the actual applications or models we'd select?
Yeah, so we broke out the data into 3 categories. On-nadir data, meaning almost directly overhead, and that is from 0 to 25 degrees. And then off-nadir data from there to 40 degrees off of a direct vertical, and then far off-nadir data beyond that out to around the neighborhood of 55 degrees.
Excellent. And if you're interested in learning more about the specific SpaceNet 4 challenge, we've had an episode with the challenge manager, Nick Weir, on this pod before. We also have, obviously, a lot of our content on our blog, and then, obviously, any of the main information you can find along with the data set on spacenet.ai. Kind of lends to the next question, Daniel. So we had the data set from 4 over Atlanta with the different nadir angles. Did we also then use the computer vision models that came out of that challenge? Or if more generally, what models did you use for this first part of the project?
The models we use are winning submissions to the SpaceNet 4 competition. These are very effective models for extracting building footprint information from satellite imagery. The 2 models we use specifically are one that was the 5th place winner from a user with the screen name XDXD, which is characterized by very fast inference times, and we use a lightly modified version thereof. For a point of comparison, since we want to know to what extent these results are specific to just a single model versus what's more generally true, we use another model from the competition, actually the 1st place winner, from a username Kanab, and there too we use a lightly modified version.
And could you explain the maybe a little bit more detail the model architectures from both XD and Canab?
Sure. So in some ways they are the same, but in many other ways they are different. So what they have that is the same is that they first generate a pixel map, which is an estimate for each pixel in the image. Is this a part of a building or not? And then from there, they trace out the polygons. They trace out the vector outlines of where the buildings are. To do that first step, to finding the pixel map, they use a UNet, which is a certain deep learning architecture that's very useful for computer vision problems like this. So in that sense, in those attributes, the models are the same. But beyond that, they start to get different. So they use two different encoders for the first part of that UNet architecture. XD's model uses a VGG16 encoder, whereas Canab's uses an SE ResNext 50 architecture. Another difference is that the latter model has a little bit more elaborate false positive rejection as a final data cleaning step at the end. And finally, for the modified versions that we use, we've pared down the former model to a single neural net, whereas for the latter model, we've pared it down to an ensemble of 4 neural nets, so ensemble versus not. So, two models obviously cannot recreate the full range of possibilities with all the architectures in the world, but these are different enough from each other to at least give a sense of whether the results we're finding are highly specific to a single architecture or if we're getting into things that are more generally applicable.
It's also worth noting that this is something that Nick talked about right in a previous pod, was that even though we had a broad array of neural network architectures in SpaceNet 4, very general similar performance in terms of per building. So even though, again, very different architectures, most buildings are either correct or incorrect regardless of architecture. So what this really means for this purpose, right, is we tried 2, but generally what we've seen is that there's similar kind of behavior among all the different algorithms. And so I think that we actually do get some variety here. It's useful to know still.
So now we're at the good part, right? So we have the data set. You guys have the models. Tell us about some of the early performance or some of the early feedback you got from your work. So how did the models do when you started altering the data set size? Walk us through that.
Sure. So kind of historically, the way the information came in was interesting. So we started by training a model with the full data set that we were going to use. Train the model, get performance, it's very good. Okay, so this is as expected. So next, we went and trained with half of that amount of data, approximately, expecting to see a big step down in terms of model performance. Train the model, and this takes a few days, you have to kind of wait. So train the model, the results come in, and it's doing really almost as well as that model that was trained with with the full data set. So, all right, that's kind of interesting. Figuring at that point, all right, how far can we take this? We'd planned to, maybe like train once more with a quarter of the data and, go back, fill in some data points, and that would be the end of the show. But we trained with a quarter of the data. It was still almost as good as the full data set. So this is getting ridiculous, right? Yeah. So just keep iterating.
I remember seeing you sitting over there in your seat and just laughing. I didn't know what was going on. I was worried about you for a little bit.
And, I was worried too because, time's going by and nothing seems to be changing. So finally, we start to see it. We start to see it turn off. We start to see performance drop down. But the real surprise was that you really have to, the range of points that you have to look at to see this full dynamic range of performance are the range is a logarithmic arrangement of points. You have to get down to a very small fraction of the total data set to start to see dramatic change.
And you've blogged extensively about these results last year in a 5-part series, and you can find all of those blogs listed on the downlink. And for a lot of this information, it's easier to convey graphically, but from just a general performance highlights, if you could just talk through how that curve looks. So let's start just with the overall. So combining nadir, off nadir, and very off nadir. How did the performance work with like a quarter and then a half? But like, when did you really see a drop off substantially in terms of performance using our modified F1 score?
Yeah, so those 3 different ranges of viewing angles all showed the same shape to the output. And that is, as you increase the amount of training data, there's a rapid rise. So when data is scarce, small increases in the amount of data greatly increase performance. But then beyond that, you get into a regime of diminishing returns, where additional data doesn't really cause huge performance gains. It causes some, but not much. So to put some numbers to all of this, for the maximum amount of data that we trained with, which was a big chunk of the SpaceNet for competition training data, something on the order of 50,000 buildings after setting aside some for validation. When training with that amount of data, you get very good performance. But a model trained on 3% of that data still gave 2/3 of the performance of training on that full data set.
And so, I mean, and I remember the first time you were showing us the early results when you were putting this all together, and I couldn't believe it. And it's always important, and this is something you've heard us talk about and repeat on this podcast multiple times, but sometimes performance isn't the whole story, right? You want to know if the information you're seeing is just statistically relevant, right? And so, once we heard those numbers, I thought, well, what's the error bars on this? What's the performance variance, if any, across the different data points? Could you talk to that a little bit?
Yeah, so that's something that was very important to us, was to do a really thoughtful analysis of the error involved, because it's very tempting, and you see it a lot with machine learning papers and deep learning papers in particular, to just post some top-line performance metrics, and that's the end of the day. And the listener or the reader is left wondering, am I even looking at something real? Am I just looking at statistical noise if you're arguing for performance improvements or differences?
And if you're trying to upset Adam Van Etten, that is the fastest way to do it, is to show him a paper with no evaluation metric description or no data available. And Adam goes from 0 to 60 pretty quick. So anyways, sorry, go ahead.
So in order to be able to answer that question, we made a point of generating error bars for our performance metrics. And the way we did that was for various representative data points. We repeated the training multiple times. That gave us a standard deviation to work with to understand how results vary with retraining. And then for the rest of the data points, we could just interpolate to get error estimates there. It ended up being very useful to have that information, because one of the things that we could find, or that we saw from that, was that with a lot of training data, model performance is very consistent. If you get a certain performance metric, you retrain from scratch, different initial random weights, maybe different images for the training data, you're still going to end up at the end of the day with basically the same performance. That's when you have a lot of training data. When you have very little, it's a different story. The performance can bounce all over the place, and we see that in error bars that start looking pretty big as you get to the left side of those plots, as you get into the low training data regime.
And there's another variable to consider when we're talking about performance and variability of that performance on the amount of data, is the amount of training time that you gave a model. Could you talk to a little bit about that and how that also affected performance, vice the size of the data set that the model was trained on?
Yeah, so in addition to looking at the total performance, or the ultimate performance of the model with different amounts of training data, we looked at how performance improved with training time. Obviously rises, gets kind of converges on a final answer. And one of the interesting things that we saw, which is, is to be expected, but it was nice to see it be illustrated, is that with small amounts of training data, the training tends to happen faster. When you're only looking at a few tiles, you can really only keep running them through the pipeline so often before you've kind of learned all that you can learn.
Well, Daniel, that was really interesting. And as I said, if you're interested in more of the specific results from this experiment, all of that is available on our blog in detail. I think what's really compelling is when you move beyond one city, Atlanta, and took this similar approach and expanding it to several different geographies, also leveraging the SpaceNet data set. I want to dig into what you did there and the results and kind of what that means. But before we do that, we'd like to take a quick commercial break. So we'll be right back. London. It's often discussed as the next future destination for an NFL team, but CosmiQ's also going there. That's right, folks. We're going there for DGI 2020 at the end of the month. We'll be there talking about our favorite topic, or at least one of our favorite topics, SpaceNet, and the availability of the data set worldwide and what data sets are going to be coming out next. And Adam, we've done a teaser, but just my memory slips. We've done electro-optical. What other data sets might we be releasing in the future? Could you remind me?
Sonar, I believe.
Oh.
Wait, no, I got it wrong. Radar, synthetic aperture radar to be precise.
Really?
Yes.
Is this the first time such a data set's been released? I believe it is.
In a large scale, I believe so, yes.
Oh my gosh. And when are we planning to do this release?
Early next year, maybe February.
Oh, that actually could line up with the conference. How convenient.
That would be convenient.
If you're interested in learning more about this conference or what we're talking about or the data set.
Or you don't have Valentine's Day plans.
Yeah, or if you don't have Valentine's Day plans, you can check out the information about the conference at DGI 2020 or obviously SpaceNet.ai for all updates as it relates to the data set and future challenges. And with that, back to the show. All right, we're back. We're talking with Daniel Hogan and Adam Van Etten about our training data model robustness study that was completed last year, looking at the amount of training data and its impact on model performance, essentially enabling us to answer the proverbial question, which is how much training data do you need? And so with that, when we left, we were just about to dive into the part of the project where you were moving beyond the SpaceNet 4 data set, so one geographic area over the United States, in this case Atlanta, and expanding it to a more geographically diverse domain. Could you explain a little bit about that structure, the data set you used, and then maybe comparing some of those results to what you found in the single city experiment?
Absolutely. So it was imperative that we looked at a broader range of locations because the results from looking at the one city were interesting, but they raised the question, is this applicable anywhere else? Have you just done a nice study of one city that is irrelevant to the wider world? And we wanted to be able to investigate that. Fortunately, we have a wonderful data set of the wider world in the SpaceNet 2 data set with imagery from 4 major world cities, Paris, France, Shanghai, China, Khartoum, Sudan, and our very own Las Vegas, USA.
And so let's just get into it. Explain some of the results when you were looking at the different cities.
Sure. So the overall shape of the curves of performance versus amount of training data were the same in each case, and were the same as seen with Atlanta, where you have a rapid rise followed by diminishing returns. And they can even be fit all by the same simple empirical model with different parameters in each case. So in that sense, they were the same, but there were also differences. The main difference, which has been seen before and was even seen in the SpaceNet 2 competition, is that some of the cities had much higher performance scores than others. When it comes to building footprint identification, some cities just represent harder problems than other cities do.
In case in point, what was one of the examples of a hard city vice easier one?
So an example of an easy city is Las Vegas. Our imagery from Las Vegas is largely suburban, which means single-family homes, all very clearly separated by yards and streets and so forth from the homes adjacent to them. It represented a much less difficult problem than, say, a place like Shanghai or Khartoum. In Shanghai, you have buildings close together. You have lots of heavy industry. You could have something like a big stack of shipping containers, which could sure look like a building, to an algorithm that's trying to learn about the world from nothing but a bunch of example images.
I think another point worth driving home is one that Daniel brought up about similar shapes, and that is, I think I was surprised. I know I was surprised. I think we all were, that we could fit a similar shape to all the curves. So to be specific, right? Daniel fit a power law function to all the different curves, and with only a couple parameters, you can do a very good job of reproducing this degradation of performance as you drop in training data, right? And it's really interesting because while we acknowledge, right, this is for the subset of problems, it's overhead imagery and building footprints. The fact that it extrapolated to all five cities in this case, right, all four SpaceNet 2 cities as well as Atlanta, implies that maybe this actually is something that's more universal, right? Maybe this is the kind of performance you'd expect from a different type of problem. Maybe if you're trying to find, cancer cells or something in medical imagery. Again, this is going out on a limb. Maybe you have something like this. It's worth exploring, right? Because if you can fit a power law quite well to your data, what that means is, if you gather a little bit of data, you get a few data points, you could extrapolate with some confidence, right, what you could get with more and more data. And this allows you to get back to the question you said earlier, Ryan, of designing your experiment. So you can say, you know what, I need X performance. I don't know how much data I need, but maybe I can start gathering data, start build training models as I'm gathering data. And then I can maybe take a guess at what performance I'll get as I keep gathering data. And then you don't have to blow all your budget on gathering a massive quantity of data. You can just maybe gather what you need for the desired outcome. And obviously we're extrapolating here, but the fact that this held across multiple cities, multiple look angles, pretty exciting that Daniel was able to actually quantify this so well.
Yeah, and it's almost something that, if you think about it, and once again, just to extend what you said, Adam, going out on a limb, it's almost, one could consider it just a necessary pre-step or research project before creating a larger data set, just a necessary business part of the business process before making an acquisition. I know that may not always be appropriate. You may already know what you need, or there already may be some workflow in place. But for those that are either getting started for the first time or thinking about a new data set that's perhaps unique to them or novel to them, that may be something that organizations should just be considering right out of the gate as a point of justification, which is, I think, would be really compelling.
I think that's exactly right. If you have even just a small amount of training data and you're wondering, is it worth it to get twice as much? Is it worth it to get 16 times as much? Then you can take this approach, train a model with the training data that you have, then train a model with half of that, then with half of that, and down the line, and you can construct one of these curves. You can get a sense, are we actually pretty close to the maximum of what we can feasibly get with the amount of training data? Or are we really data limited? Are we seeing an indication that that for our problem and our approach, there's a lot of room to grow. And being able to use these methods to have at least an informed guess to answers to questions like that can be tremendously useful for planning the next steps in any kind of data science question.
Well, guys, this was a project that was surprising throughout its entire term, and it was really compelling to kind of see what came out of it. I'd like to see us in the future hopefully extend it, maybe as we work with other data sets beyond electro-optical to see if that type of performance holds. And hopefully we'll have the opportunity to do that. But really appreciate you guys coming on the show and sharing some of your findings today. Thanks.